Electroplating is a process by which a metal or a conducting surface is covered with a layer of metallic coating by an electrical current. An article, electrolyte, and electrical current source is needed. Our article to be plated will be a key. The article must be placed on the cathode end or the site of reduction, meaning that it will gain electrons. Therefore, positive copper ions from the electrolyte solution will be attracted to the article, thus depositing a layer of copper onto the key. Because copper ions in the bath will be used and deposited onto the article, copper ions in the solution must be replaced. Therefore, a piece of copper wire will be used to act as a source of copper ions.
The wire will be oxidized. The thickness of the layer on the article depends on the concentration of metallic ions, strength of electrical current, and the time the article has been in the solution for. Platings are usually very thin, about 0.03 millimeters to 0.05 millimeters. Electroplating is often used for improving appearance, protection, to prevent corrosion, and to give surfaces a specific property.
To reinforce your understanding, take a look at this diagram. Examples of using electroplating include plating eating utensils, jewelry, machine parts, and more. The reason why it is so widely used is because it is cost effective. For example, plating silver onto a spoon is much cheaper than making an entire spoon out of silver. Since electroplating makes objects less prone to corrosion, it is often used on building materials. Electroplating is also used to make objects more conductive, making it an important process for the telecommunications industry.
There's no doubt that electroplating plays a prominent role in our daily lives. Look around you for electroplated materials. Perhaps the conductive ends of your MacBook chargers and iPod chargers were electroplated.
For our experiment, the reactants will be the key, copper sulfate solution, and a piece of copper wire. The reactants involved in the experiment include the reactions at the cathode and the reactions at the anode. On the anode end, copper wire will be oxidized, releasing copper ions into the solution. On the cathode end, the copper ion will be reduced and deposited onto the key. The products of our lab will be the copper-plated key and the oxidized copper wire.
In addition to the shown materials, we also use filter paper, 1-ring support, 1-ring stand, a funnel, a watch glass, and an oven. The reactants of this lab will be the key, copper wire, and a copper sulfate solution. To begin, we are now removing any corrosion and impurities on the key by using a piece of steel wool and rinsing it. We are now massing the key and the copper wire using an electrical scale. The mass will be used in our lab report. We are now pouring in 150 milliliters of copper sulfate solution into the 400 milliliter beaker.
Here you can see a photo of the lab setup. You can see that the key is hooked to the cathode end and the copper wire is hooked to the anode end of the power source using insulated wires and alligator clips. The power is now set to 12 volts and the timer is set to 25 minutes. As you can see, a mass of copper is now being plated onto the key. Here are several pictures that may help you understand what is going on. We are now removing the key and the copper wire out of the electrolyte bath.
Here you can see the plated key. We are now massing the copper wire and the key. Because we do not expect most of the copper to fall off the key when removed from the bath, we decided to filter the solution to obtain the mass of the fallen copper. Here we are massing the filter paper. We are now setting up for filtration. Electroplating may be seemingly harmless, but many parts of the electroplating process may not only damage the environment, but may also pose health risks. To prepare an article for plating, it must first be cleaned to provide maximum deposition. After an article is sanded with steel wool or sandpaper, it must be dipped into acids or alkaline cleaners. It is crucial that these acids and alkaline cleaners are discarded with care.
Acids and alkaline cleaners released via wastewater will undoubtedly bring harm to the environment similar to the way acid rain does. Pre-treatments also use discouraged chemicals such as fluorinated hydrocarbons, also known as organochlorides. Fluorinated hydrocarbons are especially toxic to animals and humans. For example, the infamous insecticide called DDT contains chlorinated hydrocarbons and accumulates in food chains. Baths used during the electroplating process are also harmful. For example, cyanides are often used for plating gold, silver, chromium, copper, and zinc. When cyanide baths are mixed with acid wastewaters, a deadly gas called hydrogen cyanide is released. Hydrogen cyanide is lethal because cyanide ions halt cellular respiration for organisms, a metabolic pathway by which organisms extract energy from food. In fact, hydrogen cyanide gas is so deadly, it was once used as a poisonous gas in history. The solvent and vapors from hot plate baths would also sometimes form VOCs, which significantly damages the environment and human health.
But thanks to environmental activists, regulatory laws that limit the waste produced from electroplating processes has been reduced and limited since the 1970s. Cyanide waste products are now decomposed in a two-step process where CO2 and N2 are released. Although carbon dioxide will contribute to ozone depletion, it is much less harmful than cyanides. Also, very few factories directly pump their wastewater into sewers. Instead, most baths and chemicals needed are regenerated or recycled. If they must be dumped out, factories are required to decompose them into less harmful products.